So now that we've got, we've got energy, we've got heat capacity, we've got entropy, we're getting precariously close to actual thermodynamics. And there's a big connection here that is lurking just a few steps away. I want to rewrite this expression again, minus kb times beta. That derivative, the minus derivative there was average energy. Kb times beta is 1 over temperature. And then we've got this plus kb log z. So this is the same expression as was here, just in terms of different variables. And one way that I can rearrange this is, let's solve for the kb log z. Maybe we had a system where we knew the energy and temperature, and we wanted to solve for the partition function. We would rearrange like this. That's legal. Let's multiply both sides by negative t. So negative kb t log z would give us minus ts plus the average energy per molecule, per particle. So that looks rather promising, rather leading. We've got energy minus temperature times entropy. And a bonus points if you already knew what this was going to turn into. This looks an awful lot like the Helmholtz free energy, right? U minus Ts, right? We have the identity F is equal to U minus Ts. But is this really the Helmholtz energy? I mean, it's got this weird entropy per particle, and then it's got this energy per particle. So maybe it's just a coincidence that these lined up in this way. It's not, we're not totally 100% sure just yet if this is really the Helmholtz free energy. But let's keep it in mind. We've got this potential relationship here. But it's not quite right yet, because the Helmholtz free energy is supposed to be extensive, for the entire sample of mass, and this is only like for the average per particle. So there's some still questions about maybe if you had a bigger set of entities included in your specification of the microstate, right? Instead of just saying one particle, you had 10, that you might not end up with the same easy relationship. Right. So let's try to clear that up. Kind of moving away from average values now. Have to address this issue of what do we do if we have many particles in our system instead beyond the just one small microstates. Okay, so first of all, maybe we have a system of particles where they're all identical to each other, so they all have the same microstates available, like a big collection of atoms that are all the same atom. So they're all identical and they're all independent. So each entity is in its own microstate, and it doesn't care about any of the other microstates to figure out its energy. It's just all on its own. Well, in that case, we know from the rules of statistics that our partition function would just be the product of the partition function for each molecule, right? We know from statistics that if you have two independent things and you want to find the probability of both of them happening, you have to multiply the probabilities from each one happening. So for the partition function, we also multiply that n times. So what happens if we take this and try to use our rule for calculating the Helmholtz potential from this? Well, we would get kBt and then times the log of z. That would give us minus kBt times n times the log of z1. Okay, so we could, in this situation, we could find out our partition function for just one of the particles, and then just multiply that by n, basically, to get the right expression for the whole system. This works because they're independent. Basically, what it looks like is we get a contribution to the Helmholtz free energy from each particle individually. They're all the same, and then we just multiply that by n. So that, that's good. That makes sense. But there's still then this question of what if we have some particles that are, they obey quantum mechanics and they're indistinguishable. Or if you switch their positions, if you swap their quantum numbers, you don't get a new distinct microstate. We got to be careful of that. So if we have identical particles that are not independent but indistinguishable, so they all have their own energy values, but maybe they influence the statistics of the rest. So if there's some limitation to the number of unique microstates when you have more than one particle. All right. So then what we would do for the partition function is we would again multiply all the partition functions together. So z1 to the n. But then we must account for this fact that there is fewer states that are unique compared to all the states that we can label. So we have to divide by this number of permutations n factorial. And when we take that expression and plug it into our natural log that was proposed for the Helmholtz free energy, we will get a minus kBt n. And this time we'll get the log of z1 over n plus 1. Okay, so this is still basically okay, right? We get a different contribution from each piece that depends on how much is in there, but overall it's still extensive. We've got n multiplying everything in the front. So this also is okay. It's a little weird to have this divided by n in there, but it still is okay as far as using it in thermodynamics. Okay, so there should be no problem now if we have, a system of a large number of particles of just taking the microstate of the whole thing and finding its partition function and using all of the identities we've just talked about, even though we derive them for the average value of a single entity in the system. If we specify as a microstate of the entire system, then we can use those same things as if the entire system is the entity itself. So doing this, and assuming that it maintains, the temperature. Originally, the temperature came from a reservoir, but assuming that this temperature exists nonetheless, and the whole system is what you specify with the microstate, we call this using the canonical ensemble. This is a second route to statistical mechanics. It's a sort of an alternative way to the microcanonical ensemble, and it has different rules, which I'll write shortly, and some systems it may be easier to use, and some systems it may be harder to use. But let's write out what the rules are for doing statistical mechanics in the canonical ensemble. So first, we decide how to specify the microstate of the system. We'll call that K. And we specify all possible microstates with n particles. Secondly, we need to specify how to calculate E, the energy of that microstate K. Now, K may be a long list of numbers, but we have some rule that we have to specify for how to get E. Now, these first two steps are the same as they were in the microcanonical ensemble. And the direction we went back then was that we have to figure out how many microstates give us the same energy. And that was a difficult combinatorics problem. But now, we don't have to worry about fitting the states together at all. We write all of the microstates, we specify how to calculate all of their energies, and we just go ahead and sum over all possible microstates the Boltzmann factors. Now this sum could be possible to do and simplify, or it could kind of be a dead end and we just have to calculate it numerically. But once we get this partition function calculated, that's our third step here, is calculate Z, and we suggest that you simplify it if possible, because we have more things to do with it coming up. All right, so we calculate Z. And calculating the Z like this, then, for if the microstate is the entire system and we specify all the possible unique microstates, then this method takes care of that many particle stuff that we talked about. That may come into how you decide what's a unique microstate. But here we assume that you specified all the unique microstates K and you sum up over all of them. And once you do that, then you calculate the Helmholtz free energy F using the formula F equals minus Boltzmann's constant times temperature times the natural log of Z. So we calculate Helmholtz free energy. So this Helmholtz energy is in terms of temperature. The partition function depends on temperature in some way also. It will depend on how many particles you've allowed. So depends on T and N. And summing over all the possible states, if the system has a volume, summing over all the possible states will put in that factor of the volume. So this produces a formula for the Helmholtz free energy in terms of its natural variables, F of T, V, and N. And if we have that, then all of the thermodynamics follows. Once we have F in terms of its natural variables, then we've completely specified that thermodynamic model. So it's a very slick way to go from a statistical model into a thermodynamic model. And it's so simple kind of in terms of the equations, right? There's not like a bunch of crazy integrals or derivative equations to solve. You don't have to work with a bunch of factorials. The only real hard part is maybe doing this sum, simplifying this sum if you can. But it's so slick, you kind of tend to wonder, does this really work? Is this really going to give us the right answers? Is this going to match up with what we know from before? And how does it actually, how does this actually end up working? So let's put our new ensemble to the test and proof it with some examples. So I've chosen an example that's kind of fun to do in the canonical ensemble. It's the Einstein Salad. if there are any spots left in your mind at this point to remember stuff, I'll be proud of you. If you remember the Einstein Salad, that's even better. So remember the model was we put a certain number of energy quanta in each atom in the solid. There's n atoms, and so to specify the state of the system, we've been calling this our K value, right? We would specify, say, the number of excitations in atom 1, the number of excitations in atom 2, the number of excitations in atom 3, and so forth. We have to basically give the number of excitations that are residing on every oscillator in the system. So we have a long vector of n components, and all these q's are positive integers. So they could be 0, 1, 2, 3, 4, 5, up to infinity, but not negative and not fractions. All right, once we do that, our energy of that state is equal to the sum of all the q values. So we'll say this is over oscillator J. So h bar omega is our energy unit, and we sum over the quanta present in each oscillator. So J would be the number of the oscillator, or the number of the atom. So J is 1 up to J equals n. Right, and we had just said, well, since we add these all together and they're all just integers, we could just call that the total number of quanta q in that microstate. But now, instead of trying to figure out how we could possibly arrange these different values of q to end up with the right total number of quanta, we're going to just kind of ignore that in this canonical ensemble and say, well, we know how to specify all the states, so we're just going to take the sum over all possible microstates of the energy of that microstate in the exponential divided by kt with a minus sign. Okay, so this exponential here in this sum, now it takes a little bit of thinking to see what does it mean to sum over all microstates when each microstate is defined by a large set of integers. Well, every different possible combination of integers from slots 1 to n is a unique microstate, right? So what we really can do here is we can say, well, the value for q1 could range from 0 to infinity. The value for q2 could range from 0 to infinity, and those would all produce unique microstates. So our sum here over k is really talking about a sum over q1, a sum over q2, a sum over q3. This is all the possible ways to give any q values that would be different from each other. And they can go all the way up to infinity. We sum over all possible microstates here. We don't worry about the sums converging. That will happen because of the exponential. And then what we put in our summand is the sum of all of the energies, or the total energies. So sum of h bar omega times, well, we'll have q1 plus q2 plus q3 plus dot, 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 all the way up to qn. So we have a large sum actually in the exponential for the energies. Okay, so the first time you see this thing, you might think, oh gosh, we've got 10 to the 23rd sums to do. How can we possibly ever simplify this? Well, just settle down and take a look at what's in the exponential here. It's just a linear sum of q values. And one of the rules of exponentials is the exponential of a sum is equal to the product of exponentials. So actually, each one of these sums is identical, right? If we separate out the q1, we'll get e to the h bar omega q1 over kt times the rest of the exponentials. We can pull that into the q1 sum. And so this is essentially the same as any q from 0 to infinity exponential of minus h bar omega over kt times q. This sum done and multiplied by itself n times. Now, I will definitely forgive you if this was not the obvious simplification to make here, but it kind of tends to happen in these canonical ensemble questions when you can actually solve it. You have independent particles, they have energies that add, and you can move these into the individual sums and get a lot of copies, basically. So how can we do this sum? Well, we've got raised to the n power. We can take care of that later. Let's think about just the sum inside the square brackets. We've got an exponential of things multiplied together. And now we're going to use another property of exponentials, as if you take the exponential of a product of two things, that's equal to the exponential of one of them, the whole quantity raised to the power of the second. So this is the same as e to the minus h bar omega over kt, all raised to the q power, right? If you have these chaining successive powers, then the powers multiply. And then that whole sum would be raised to the n power at the end. Okay? So now we're in a pretty good position here, because what we have for our sum is basically a geometric series, right? A constant that doesn't depend on q at all. This constant is raised to the q power. So that sum is equal to the geometric sum result 1 over 1 minus the constant. And then that's all raised to the nth power. All right, so there's our expression for the partition function of the Einstein Salad model. 1 over 1 minus exponential of minus h bar omega over kbt, all raised to the n power. All right. It's not as bad as we might have thought. But still, does this really give us the answers that we know and love for the Einstein Salad? Our next task is to calculate the Helmholtz free energy by taking the negative logarithm of this. Right? And so what do we get here? Well, we have minus kb t. The n comes down, and then I have log of what's inside. And I tend not to like having logs of fractions if I can help it, so we'll take that implied negative 1 power and use it to get rid of the minus sign in the front. So 1 minus e to the minus h bar omega over kt. Okay. So here's our formula for the Helmholtz free energy of the Einstein Salad. And at some point in the past, we may have calculated this by a different method. You can check, you can verify that that is the same. Now we could continue to check here by taking the various derivatives, right? df dt should provide us with the opposite of the entropy. And what we would get from that is a nk times minus natural log of this 1 minus exponential stuff plus h bar omega over kt times 1 over e to the positive h bar omega over kt minus 1. Sorry, so this is not a mistake. This one is positive. After you do that derivative, there's temperature here, You've got a lot of chain rules to do because there's a bunch of functions stacked up. Here, log, subtraction, exponential, division to get to temperature. But this is what we end up with for the opposite of the entropy. And this might not look so familiar to you either, but hopefully we can get to a more familiar expression. If we take this model and try to get its formula for internal energy, we would take F then plus Ts. Right, do that transformation in reverse. And if you add these together, here's F right up here. Here's S down here, well, minus S. So if we were multiplying this by T and adding these together, these two first terms would cancel, and then we would just end up with N H bar omega over this fraction. So E H bar omega over KT. Okay, and that's our old expression for the internal energy of this Einstein solid in terms of temperature. All right, so it actually does work, and we don't have to think hard about, ways of combining things or factorials or binomial coefficients. We just have to, be good with our summations, and we can work in this canonical ensemble. It can be very powerful. All right, but it wouldn't be worth developing this method of doing statistical mechanics unless it enabled us to solve some new problems that we couldn't solve before. So we're going to tackle one of those in our next example. And even though this one is a little bit heavy on the variables, I do want to put it up here because it does a great job at justifying a lot of the hand waving that we did earlier on in the course when we dealt with ideal gases that were not monoatomic. So we're going to now use our newfound powers of the canonical ensemble to calculate the model for the ideal diatomic gas. So how do we specify the microstate for the ideal diatomic gas? Well, we have N molecules. For each molecule, we specify a center of mass momentum, px, py, pz. Three-dimensional vector, continuous variables. And for each molecule also, we specify an L value for its rotational quantum number and an M value for its Z rotation quantum number. Remember that the L can be an integer that's positive, and the M can be an integer that is smaller than L in absolute value. Now the ideal diatomic gas molecules, if we took two molecules that had a set of P's and two L and M's, and we swapped them with each other, right? And we swapped all of their numbers for each other, then that would not result in a unique microstate. So even though we have N molecules, giving two molecules, say, a swapped version of these basically quantum numbers would not result in a unique microstate. So here we have a situation of identical, indistinguishable particles, and the state of the particle is set by 5 values. So let's calculate the partition function for just one of these. We do also have to specify now the position of the particle. Each position could result in a different microstate as well. Okay, so for our partition function for just one molecule, we'll be integrating over x, y, and z. We'll be integrating over px, py, pz, and we'll be summing over L, and we'll be summing over M. Kind of the the activity of the day with partition functions is having really long sums, or a large number of sums. All right, and the thing that goes into the summand is the exponential of the energy over kT. So I'll have minus p squared over 2m kT minus h bar squared L plus 1 over 2I kT. So that will give me the partition function for just one of the molecules. All right, and that's exact. Now it's a matter of mathematics whether we can work out these integrals or not. Let's try to do that. Okay, the first one here is very easy, dx dy dz. We're going to assume that there's some limits to where the particle could be. So this integral over these three axes will just give us the volume of the system, the volume of the region of space where the particle is allowed to be. Okay, then these three integrals over momentum. All right, we can treat this as a three-dimensional integral, and it's an exponential integral. It's actually one of those Gaussian integrals, right? Because we basically just have a Maxwell distribution here for the translational momentum. So we'll look at that separately. And then here we're going to have a sum over L and M. Now the sum over M is trivial, right? There's no M's over here. I mean, there's a mass. That's not the same. There's no M quantum numbers in here. If there was a magnetic field, then there might be some energy due to that from M. But there's not any right now. So we will take we'll do this M sum. It will give us 2L plus 1. That actually, you can think of that degeneracy there. And then we'll have the exponential of minus h bar squared L plus 1 over 2I kT. Reminder there, I is the moment of inertia for the diatomic molecule. Thermodynamics does not predict that, just like it doesn't predict the mass. Okay, so one thing to add in here that we have to do when we use continuous variables, this doesn't affect the thermodynamics so much, but it does influence the units. The partition function is unitless, right? And a volume times a momentum is not. So to satisfy that, what we do here is we usually, this is somewhat semi-classical anyway because we're specifying a continuous momentum, but we divide by the volume and phase space, the minimum volume per particle, which is h bar, right? Delta p times delta x is h bar. So that's our minimum volume. That doesn't affect the thermodynamics, but it does make us get the right units. Okay, so now we have a couple of integrals to work out. The first one here over momentum is basically just a Gaussian integral. It's a three-dimensional integral. It's got minus p squared times a constant. So that will be equal to pi divided by the constant to the 3/2 power because it's a three-dimensional integral. So that's that one. That's done. Now the second one here, the sum. Now this sum we cannot do this sum exactly. We just can't do it exactly. It looks like we've got this exponential here is L times L plus 1. There's not really any hope. So if we were going to persist in being exact here, we would need to sum this up numerically, right? We would need to sum it numerically. So what do we do now? I'm not going to pull out the computer and start doing a numerical program to sum this up for you and plot it. But one one approximation we can make to proceed at this point is the high temperature approximation. If the temperature is large compared to the energy level spacing here, that the energy levels are h bar squared L squared basically over 2I. If the kT is much larger than that, then this quantity, right, this exponential is going to vary very slowly. The t is large, so the L's changing in the numerator just kind of keep us changing by a very small amount. So this is what this exponential would look like versus L. And if a t is large, then it makes this much wider compared to an integer spacing. So if we're at low temperature, then there might be only like 3 or 4 or 5 L integers that matter here. If we're at super low temperature, then you could maybe only take 1 or 2. But if we're at high temperature, then many different L values will contribute, and it may be high enough temperature that we can replace this sum with an integral. So basically, this is the approximation that we have large values of L. So we would integrate of dl from 0 to infinity. The 2L plus 1 does not really matter because L is supposedly large, so we'll just change that to 2L. The L plus 1 in the exponential also doesn't really make a difference since L is already large. So I'll have this integral to do if I have the high temperature limit. Now, integrals versus sums, it's not always better to make it into an integral, but in this case it is. So this integral we again can calculate. It's a Gaussian integral. It's got an L squared in the exponent, and this time it has a 2L out here. So the answer will be a little bit different, but nevertheless can be looked up for its general formula in some tables. Okay, so I'll rewrite these first terms. And then this integral over the L values here will end up giving us, turns out to be 2I kt over h bar squared. Right, just basically this equals the inverse of the coefficient in the exponent. Okay, so there's our partition function for just one molecule in the ideal diatomic gas. So we're now well on our way. We've got, it's got a lot of variables in it, but this is relatively simple in terms of a formula for a partition function. There's no remaining sums or integrals. It's all just powers and multiplication. So we'll be able now to calculate our partition function for the entire system, because this is a system where there is multiple particles. This is just for one. So we'll be doing the formula for independent, indistinguishable particles. So we'll have 1 over n factorial times this stuff to the nth power. So the way I got this set up is to distinguish what's kind of important here for thermodynamics and what's really not. So here we could have a 2 pi mk over h squared. That would come from this term. That's to the 3/2 power. A 2I times Boltzmann's constant over h bar squared. All that stuff is all just constants that specify the microscopic properties of the molecule, right? Mass, moment of inertia, Boltzmann's constant, Planck's constant. That's all raised to the n power, which is not very interesting. So then we have temperature is here to the 3/2 and 5/2. So we'll have temperature to the 5n over 2. since we raised it to the n. And then we've got volume here. It will be volume to the n power. All right, so there is our partition function for the ideal diatomic gas in the high temperature limit. Okay, so we'll just call all of this stuff in here, we'll call this some constant. We'll denote that as A. That depends on the microscopic properties of the molecule. This would basically influence your Gibbs energy of formation from the table, but not like the ideal gas behavior. Okay, so to finish this off, we're just going to take the logarithm of this multiplied by kT to get the Helmholtz free energy. All right, so when we do that, it's going to be pretty straightforward. Here we'll have minus kT in front. The factorial term is going to give us n log n minus n. This term is going to give us basically plus n log a. For the temperature, we'll have 5/2 n times log of T. And for the volume, we'll have n log V. So that's the logarithm of the whole thing. And we'll put this together. We'll have minus ktn times logarithm of, let's see, what's going to go in the, so the n's are out front. What's going to go in the logarithm is a factor of a factor of t to the 5/2, a factor of v, and a factor of n on the bottom. Oh, this is minus because that was n factorial in the denominator. So that's that, and then a plus 1 from this n here. Okay, so that's our Helmholtz free energy model for the ideal diatomic gas. And you can do all sorts of checks from this. Doing the derivative with respect to volume will result in the ideal gas law. Doing the derivative with respect to temperature will give you the entropy. And doing the derivative with respect to n will give you the chemical potential. Last thing you can do here for fun is after you do those derivatives, go and calculate the internal energy by taking F plus Ts, and you will no doubt get 5/2 NKT. Okay, so this example really shows you kind of what the canonical ensemble allows you to do. We can handle these more complicated systems with kind of less normal energy spectrum. We don't have to think hard about how the energies combine to produce a total. We just toss them all into the mix with that Boltzmann factor and work it out. It also gives us, in terms of the ideal gases, it now gives us this perspective. Both the mass and the moment of inertia now play into the chemical potential value for the ideal diatomic gas. And we can see why this, why the heat capacity ends up at 5/2, because there was a T to the 5/2 n here, because there was a T from the translation, and a T that came out of the rotation integral. Right? It also gives us this perspective now about why the, why we kind of did a little bit of hand waving earlier on in the course, saying that the ideal diatomic gas had 5 degrees of freedom, because it only has 5 degrees of freedom if the temperature is high enough to allow all sorts of rotational motions to be randomized throughout. If it's cold and there's only a few ways to rotate, a few L values allowed, then it won't have this. It'll tend closer to a 3/2 NKT for its internal energy. Act more like it can only translate and not rotate. Okay, so that finishes our example for the ideal gas model. Okay, so we kind of impressed that we got the right answer for that ideal diatomic gas. We get a little bit more insight into why it comes out that way and when it might not work. But we'd like to be a little bit, able to make some general conclusions about more complicated systems now. And we're going to be able to do this by proving a theorem which was mentioned at the start of the class. But now we really have the machinery that's necessary to prove it. So this is called the equipartition theorem. So we're going to be very general now. Suppose there is a continuous degree of freedom Q. And this degree of freedom produces an energy, E of Q, that is equal to some constant, C, times Q to some power, P. So extremely general here. Like this could be 1/2 mv squared for kinetic energy, right? 1/2 m would be the constant, the power would be 2, or it could be any other kind of weird form of energy. The power might be 1, the power might be 3, or something like that. But just still a power law for this energy. And a degeneracy of the state Q with equal to A times Q to the K power. Right? So there's, at a given value of Q, there might be a certain energy, but then multiple states that give that energy too. So the partition function then of just this entity, this degree of freedom on its own, would be to integrate over Q, over all possible values of Q, times the degeneracy function times e to the minus e over kt. I'm going to write this as a beta. Beta EQ. Okay, so this would turn into integral over q of a q to the k times exponential of minus beta c q to the p. Okay, so that would be our general partition function for this extremely general degree of freedom. So if we have this, if this is just part of some larger system, then the partition function of the whole thing would be this times the partition function of the rest. So it's fine to just look at this for that one degree of freedom on its own. So let's try to do this integral here. It looks pretty horrible, but we'll find out that there is a way to do this that's not too hard. We'll let x be equal to the exponent, so beta c q to the p power, right? So if we do that, then our value for dx will be, we're just doing a substitution here for the integration variable. So we could probably work this out just as an exercise. That'll be dx will then be beta c times p times q to the power p minus 1 times dq. Right, and if you put those two things together, because we got to eliminate dq, right? So dq will be q over p times x over beta c to the 1 over p power times 1 over x dx. Unfortunately, that's what it comes out to if we do this kind of substitution. All right, so when we do our calculation for the integral here, then we're going to have dq, well, we're going to change this to a dx. So the a stays out front. The dq becomes all this stuff. No, sorry, there's not a q here anymore. This stuff is the q. So there's a dq is 1 over p x over beta c to the 1 over p power times 1 over x. Then there's this q to the k power, which is the degeneracy, so that's going to be x over beta c to the k over p power, and then our exponential becomes simple because we set that up to be the exponent. So we have this integral to do, and it's it's not really a very easy integral to find the value of, this x to all these fractional powers, but we'll find out that doesn't really matter. So look at the following things here. So we've got a divided by p, then we have quantity 1 over beta c to the power k, so power k plus 1 over p. So k was the power of the degeneracy, p was the power of the energy. So that all stuff is outside the integral. Then the only things left that depend on x here, we've got x to the 1 over p power plus k over p power, and then a minus 1 power e to the minus x. So you can look up values for these kind of integrals with these fractional powers of x, but it doesn't really matter because this whole thing is just basically some constant that depends on p and q. And what we want to do is look at here how the energy of this degree of freedom gets distributed. So we'll look at this. We'll take the log of this partition function. And a and p are constants. The c is a constant. So the only term here that really is going to make a difference is this k plus 1 over beta, k plus 1 over p. And then we'll have a minus log of beta. And then other constants that don't depend on beta. All right, so the reason I don't care about those other constants is because when I go to calculate the average energy of this degree of freedom, I'll be taking negative d beta of this log of z1, and that will just come out to be k plus 1 over p divided by beta. So remember that beta is just the temperature, right? So our average energy for this degree of freedom will be this fraction k plus 1 over p times Boltzmann's constant times temperature. And that simple result is the equal partition of energy theorem. So it's amazing, right? It doesn't matter like what the energy actually comes from. It doesn't matter what the constant is here. It doesn't matter what the constant is here. You don't actually have to say anything about how it's actually distributed. If you look at the average energy of this type of continuous degree of freedom, it's going to be some fraction of kT. When we talk about kinetic energy, the k value is 0. They're not degenerate at all. And the p value is 2 because it's mv squared. The 2 is the power of v. So we get 1/2 kBt for the average energy of a velocity degree of freedom. For rotation, we also had L squared is the main thing that determines the energy. So our power would again be 1, but we have a degeneracy for those states. We have a degeneracy that is proportional to Q, proportional to L, right? The 2L plus 1 proportional to L. So it has a value of 1 for the K, and then we have 1 plus 1 over 2. So the average energy of a rotation is just kT. We can apply this further on to vibrations. A vibration has a single coordinate that determines its potential energy, and a single velocity or speed that determines its relative motion at that time. So it's got two coordinates, 1 with some constant times distance squared, and 1 times some constant, a different constant with velocity, relative velocity squared. So we'll have no degeneracy, so a 0 and a 1 over 2. So we get 1/2 kT for every position degree of freedom in an oscillator, and 1/2 kT for every velocity degree of freedom. So for every type of vibration that we have in a molecule, we get a factor of 1 kT. Right. Okay, so that's a very general theorem that used to justify a lot of the things that you that you get told in chemistry courses or early on in thermodynamics about how there are these molecules, and since they have this way of rotating and vibrating, this is what their heat capacity should be. But now we can actually prove this from the canonical ensemble, its partition function, and these derivatives, exactly what the average energy of that degree of freedom will be.